Hello everyone. In this lecture, we will discuss about the Gibbs phase rule. It is an important rule in phase diagram which relates the number of phases in equilibrium with number of components and the number of degrees of freedom. In Gibbs phase rule, the P represents the number of phases in equilibrium. C is the number of components present in the alloy system which we are under considerations. And we can define a quantity called the degree of freedom, which is represented by F. So before discussing about F, the degree of freedom, let us discuss what are the thermodynamic variables for Gibbs phase rule. There are two thermodynamic variables. One is the pressure and other one is the temperature, which both can be variables. But most of the cases we fix the pressure at a one particular atmospheric pressure, mostly one atmospheric pressure, so that mostly there will be one thermodynamic variable. The second type of variables involved are the composition variable, and the relevant compositions variables are the phase compositions. Overall alloy compositions which is not a variable except when we have single phase equilibrium where the alloy composition is also the phase compositions. So we only consider the phase compositions plus the thermodynamic variables, that is the mostly temperature alone. So that next is the number of compositions variables. So we just mentioned the phase composition is the mostly considered as the composition variable, and if there are C components present in the alloy, so that one need to specify C minus 1 compositions. If there are C components, we need to specify C minus compositions for each phase, and if there are P number of phases, the total number of compositions variable will be P times C minus 1. So where C is the number of components. So P into C minus 1 is the total number of compositions variables. So that the total number of variables will be, we can represent it as V, and it is equal to P into C minus 1 plus 2 if both pressure and temperatures are the variables, if P and T are variables. And we can also write V is equal to P into C minus 1 plus 1 if only temperature is the variable where pressure is kept as a constant. Now we can define what is the degree of freedom. When phases are at equilibrium, there are equilibrium conditions. Those equilibrium conditions are where F is the number of thermodynamic variables which can be specified independently without changing the phases in equilibrium. That is how we define the number of degrees of freedom F. Since there is thermodynamic equilibrium, there are equilibrium relations between the thermodynamic variables. So if we specify certain number of variables, others are automatically fixed by these equilibrium relations. That is, if we have a many number of variables, we represented as V, the total number of variables, and if we fix some of the variables, and then if you are specifying, okay, if you are specifying certain number of variables, then other variables are automatically fixed in order to have the equilibrium conditions. So this is what is the basics for the Gibbs phase rule, and the Gibbs phase rules states that and it gives this following equations where F is equal to C minus P plus 2 if both pressure and temperatures are variables, and F is equal to C minus P plus 1 if only the temperature is variable where pressure is fixed. This is applicable for the binary phase diagram. So the F is the number of degrees of freedom which will be always less than or equal to total number of variables. So if you are going to specify certain number of variables, that is the number of degrees of freedom, then automatically some of other variables going to be fixed, provided in order to have the equilibrium conditions, and that value, the number of variables which can be specified, it will be always less than, or some cases it can be equal to the total number of variables. Since there is okay, hence the Gibbs phase rule provides a device for testing multi-phase equilibria and deciding the number of variables, that is the number of degrees of freedom necessary to define the energy state of the system. In order to make it much more clearer, we are considering an example of tin lead alloy system, and here in this figure you can see the tin lead phase diagram, and we have seen one example of phase diagram in the last lecture. Just like that, here on the y-axis you can see the temperature in degrees Celsius, and in the x-axis, that is the composition axis, composition variable, that is the weight percentage of tin. So left side it is lead, and the right side it is tin, and you can see different phases which are in equilibrium. At low temperature it is in the solid form, and on the left hand side you can see alpha Pb, that represents the solid state of the lead medium, and on the right hand side you can see beta tin, so that is the solid state of the tin, and on the top portion you can see that is in the liquid phase. After the liquidus line, this is in the liquid state, and I represented that equilibrium state as 1, that the red color, red fonted 1, and the 2 I represented here, that is an equilibrium between alpha plus L. So that is the solid state lead is in equilibrium with liquid phase in that region, and on the right hand side you can see beta plus L, where the liquid phase is in equilibrium with the solid tin, and so on. And now we are considering different cases. The first one we will consider the single phase L in equilibrium. That is, we represented the top portion of the phase diagram, and I represented as 1. So in this single phase L equilibrium, since there is only a single phase liquid phase, the compositions variables will be Cl. So there is only one compositions there, that is the liquid alone. So that is we represented as Cl, C suffix L, and the temperature. So there is another variable is temperature. So the total number of variables we can represent, that is V should be 2, the temperature and the composition of the liquid. So according to the phase rule, the degree of freedom is F is equal to C minus P plus 1, because here we keep the pressure a constant, so that is why there is plus 1. So that will be equal to 2, because C, the number of components here is 2. There are tin and lead components are there, so that C is equal to 2, P is equal to 1, P is equal to 1, because this is a single phase state. So 2 minus 1 plus 1, that will be equal to 2 minus 1 plus 1 is equal to 2. So that is the total number of degrees of freedom is 2. It tells us that in a single phase equilibrium, we are free to specify both the variables, the temperature and composition Cl. We can vary the temperature and composition independently in the single phase equilibrium. So even if we vary both the temperature and compositions, the system will be in equilibrium state. So that is according to the phase rule. Now we consider the second case, that is I represented in 2. The 2 number is there, so that region. So where the alpha and L is in equilibrium, alpha plus L. So that is a two-phase equilibrium. So here we have compositions of both phases. So we'll have the compositions of liquid Cl as well as the compositions of alpha. So that is represented as C alpha. And there is another temperature variable is also there. So the total number of variables now increases to 3. Previously it was 2. Now the total number of variables becomes 3. Now we will see what will be the degrees of freedom. So F is equal to C minus P plus 1. Here C is again 2, 2 components. Then P is equal to 2. Now the phases, the number of phases is 2. So 2 minus 2 plus 1. So 2 minus 2 plus 1 is 1. So that means although the number of variables is increased, the number of degrees of freedom is decreased to 1. Out of 3 variables, we had 3 variables, the compositions of liquid, compositions of alpha as well as the temperature. Only one of them can be specified and the other two will be determined by the equilibrium conditions. So we in this case the degrees of freedom is 1. That means we can only specify one of these component. We can either specify the temperature or the alpha Pb or alpha liquid. Then sorry, we can only specify temperature C alpha Cl. Either one of these components can be specified and the other two will be resulted by the equilibrium state. Here you just imagine that in that particular region we keep the temperature a fixed one. So temperature if fixed means the axis, we can draw a line horizontally along this region, and on the left hand side there will be C alpha, and right hand side there will be Cl. So once we fix the temperature, we can only have one fixed values of C alpha and one fixed values of Cl. We cannot have different values of this one. So that is what is we inferred from the Gibbs phase rule. Now we consider the three-phase equilibrium state. So three phases are in equilibrium. So that means we will have four variables. So what are the four variables? That is the compositions of this C alpha. In this case, the C alpha is there, Cl is there, as well as C beta will be there. So these three compositions variables are there, plus there is temperature. So there are four variables, and according to the phase rule, the degrees of freedom will be F is equal to C minus P plus 1. Here C is equal to 2. The components is 2. P, the number of P value, the phase number is 3 plus 1. So 2 minus 3 plus 1 is equal to 0. That means there is no degrees of freedom. So that means in a three phases in equilibrium state, we are not able to vary any of the four variables. So we cannot specify any of these four variables, but this will be fixed. So in this particular diagram, you can see the central horizontal line in which we have a fixed values of C alpha, Cl as well as C beta. So that is the that represent a eutectic horizontal line that is three phases are in equilibrium. So the corresponding temperature can be we can find out by extending this horizontal line. So this horizontal line means there is an horizontal line means there are these three phases are in equilibrium. So this is what is we inferred from the Gibbs phase rule. In order to make the last slide much more clearer, I'll try to explain it once more. So this is the temperature, the phase diagram, Inlet phase diagram. So y-axis is the temperature, on the x-axis is the compositions, and left side it is lead and right side it is tin, and the weight percentage of tin is drawn along the x direction. So alpha represents the solid state lead, and beta represents the solid state tin, and this is alpha plus beta is the net alloy formed, alpha plus beta, and liquid L is the liquid state, which is the uniform liquid state, a single phase equilibrium state. L plus alpha is the equilibrium between solid state alpha lead and liquid state, and L plus beta is the equilibrium between beta and L. So last slide we describe three cases. One is the single phase liquid. So that is this one, this top portion. So in this case we find out that the degrees of freedom, the compositions is Cl, and composition variable is only Cl, and there is another one variable is temperature. So there are two variables and degrees of freedom is 2. So that means if you vary both variables, so in this case we can vary the compositions. The compositions can be varied. We can also vary the temperature. So even if we vary these two independently, the system will be in equilibrium. So that is meant by the first case. So we can independently change either the compositions or temperature. It doesn't affect the equilibrium state. In the second case, we consider the two-phase liquid plus solid, L plus alpha equilibrium. So that is this region. So in this case, we find out that the degrees of freedom is 1. So here we have three variables, that is the compositions L, Cl, C alpha, and temperature. Temperature is also a variable. So in this case, we can only specify one variable. So degrees of freedom we obtained is 1, means we can only vary one variable. For example, if we fix the temperature here, so this line represents a temperature. We fix the temperature to this particular value, so that we'll get one C alpha this side. So this is C alpha. This is C alpha here, and you'll get a Cl here. So this will be Cl. So that means if you specify any of these one variables, any one of this any one variable out of these three, the other two are fixed in order to have the equilibrium conditions. So that is meant by the second case. In third case, we consider all these phases are three phases are in equilibrium. So alpha case is in equilibrium with liquid and beta. So three phases are in equilibrium. So that means we find out that the degrees of freedom F value is 0. That means we cannot specify any of these variables. So in this case, this horizontal line, this central horizontal line, this line represents the three-phase equilibrium. So here this is the C alpha. On the left hand side, this is C alpha. This is C alpha. This is Cl. The central is Cl, and this is C beta. Right hand side, this is C beta. These all are at the same this is all fixed value for this horizontal line, and correspondingly there is a temperature on this side. So that is called the eutectic temperature. So either one of these variable we cannot specify, all are fixed in order to have the three phase equilibrium.